Now I will give you one problem for practice and also the procedure how to solve this problem by using moment distribution method. So during the earlier lecture, due to the battery, I have to stop the lecture in between. Now let's continue. So this is a sway type frame. So this is a sway type frame, and the analysis of sway type frame is to be carried out in two stages. So the first is Nonce analysis. Non-sway analysis. Now assume that the sway of the frame is prevented by applying resisting force RF. So here RF is applied and the sway of frame is prevented. Now Nonce analysis, first step, find out fixed end moments. So now here the heights of the columns are different. So we will calculate for AB and CD separately fixed end moments. So this is due to loading. MF AB equal to minus WAB square by L square, that is 25 into 3 into 2 square upon L square is 25. So minus 12. So MF BA equal to plus 25 into 3 square into 2 divided by 25. So this is 80 kilonewton meter. So due to external loading, let's find out fixed end moments for all the members. Then beam BC, MF BC equal to minus, this is central load, WL by 8. So 40 into 4 divided by 8. So this becomes minus 20. Then MF CB equal to plus 40 into 4 divided by 8 equal to plus 20 kilonewton meter. This is for member BC. Then CD, MF CD equal to, this is UDL minus WL square by 8. 6 into L square 9 divided by 12. So this is minus 4.5 kilonewton meter. Then MF DC equal to, this is plus 6 into 9 WL square by 12. This is plus 4.5 kilonewton meter. So now we have calculated fixed end moments. So next step is find out distribution factors, say at joint B. So at joint B and C we have to calculate the distribution factors. So at joint B, so KBA at B towards A, further end A is fixed. Stiffness of BA, that is 4 EI divided by 5. This divided by 4 EI upon 5 plus 4 EI stiffness of BC, that is 4. So stiffness of BA divided by stiffness of BC plus stiffness of BA plus stiffness of BC, total stiffness at the joint. So this is 0.44. Then KBC towards C, it is 1 minus 0.44, 0.56. Then next, let's consider joint C. KCB equal to stiffness of CB, it's 4 EI upon 4 divided by 4 EI upon 4 plus, this is 3 EI upon L, because end D is hinge, support D is hinge, therefore 3 EI upon L is 3, so this we get 0.5. KCD is 1 minus 0.5, so 0.5. So we have calculated fixed end moments as well as distribution factors. Now let's prepare a table, moment distribution table for Nonce moments. So this is, you just enter the values of calculated distribution factors, 0.44, 0.56, 0.5, 0.5. And the fixed end moments, here it is minus 12, this is 18, minus 20, 20, this is minus 4.5, and this is plus 4.5. So now we have entered the distribution factors. Now this is end D is a hinge support and bending moment at D must be equal to 0. That is release of bend moment at D and carryover. So apply equivalent opposite, carryover minus 2 point, this 25. Now say mark one line and this becomes 0, and this is minus 12. So double line you take because now we are taking summation here, and these are called initial fixed end moments. So this is minus 20, 18, this is plus 20, and this is minus 6.75. So these are the moments. Now we have to start balancing carryover, balancing carryover. So after doing all these steps, so find out here unbalanced is negative, balanced is positive. This is negative means balanced is positive. This unbalanced is positive, this is negative, negative. Then you carry over this moment, and this moment by half value with same sign. But this cannot be carried over because end D is hinge support. Then again you do this balancing. This is minus minus. This is plus minus minus. Again you mark a line. Again carry over this moment by half value with same sign. Then this is to be balanced, and then see how many steps are required in order to balance the joint or to vanish the moment, unbalanced moment. So again this is to be carry over to the next support by half value, and remember whenever you want to stop, you balance and stop. This is plus plus, minus minus. Let us say these cycles are sufficient, then you mark here double line and take the summation under each of the supports. So this gives us Nonce moments. These are Nonce moments. So these values are Nonce moments. Now the first part, after getting Nonce moments, find out RF. So how to find out? Oh, just a minute. Okay. Now this is Nonce analysis. So now to find out RF, we have to use summation fx equal to 0 because RF is acting horizontally, total shear in column must be equal to 0 using this equilibrium condition. So let's find out RF. Now to find RF, so we have to use the equilibrium condition, that is summation fx equal to 0. Here see HA plus HD plus 25 minus this 6 into 3 and minus RF equal to 0. So simply summation of x equal to 0. Sum of all horizontal forces acting on frame must be equal to 0. That means the value of RF, if RF is taken on the right, is equal to HA plus HD, and this is 18, 25 minus 18, 7. This is plus 7. Plus 7. Okay, means now HA and HD are required. So how to find out HA? Sum of column end moments MAB plus MBA. Now there is a load on member AB. Load is acting on the member AB. Take the moment of this load about B. If it is clockwise, take positive, anti-clockwise, take negative. Because this is now anti-clockwise about B, so negative. And we are calculating this HA by taking moment about B and HD by taking moment about C, remember. And this is anti-clockwise, minus 25 into 2 divided by height of that column plus. Now HD, sum of column end moments, MCD plus MDC. Now there is a load on the member and the moment due to load about C is clockwise. So this is plus 6 into 3 square upon 2. And this divided by height of the column, that is 3. And this plus 7 is there. Plus 7 is there. So now it's very simple writing down this equation to find out RF. Now what is this MAB? This value substitute along with their sign. MBA is this value. MCD is this value and MDC is this. DC will be 0. Remember, MDC will be 0. So this is 0. Whatever other values you just substitute and find out RF. Now here the first part of the problem is completed. I hope you will do this calculations. Now the second part, B, this is sway analysis. Sway analysis. Now we assume sway towards right. MFAB equal to MFBA equal to. Now due to sway, that we know, due to sway towards right, the fixed end moments at end of columns will be minus 6EI delta upon L square at the end of each column, but heights of the columns are different. Therefore, we will calculate separately. For AB and CD, we will calculate separately. Now this is MFAB equal to MFBA minus 6EI delta upon L square is 25. So what I will do, let's assume EI delta equal to 25. Any value we can assume, remember. 6 into 25 divided by 25, this is minus 6 kilonewton meter. For first column AB, we got the answer. Now next, MFCD equal to MFDC equal to minus 6 EI delta upon L square, that is 9. L is 3, 9. But EI delta don't change here. EI delta it keeps same. Once we assume EI delta equal to 25, the same value is to be used here. So this is equal to minus 6 into 25 divided by 9. So this is minus, what you will get this as 16.66. 16.66. So now these are the fixed. See what happens when heights are different. So we get here for AB, column AB minus 6 kilonewton meter, and here minus 16.66 kilonewton meter. Means if the height is less short, so that moment will carry more moment. So then, so next is prepare a moment distribution table, because distribution factors we have calculated during Nonce analysis. Now prepare a table once again here. So you write the same distribution factors, 0.44, 0.56, and here it is 0.5, 0.5. And the fixed end moments at the ends of the columns. For AB it is -6 here, -6 here, -16.66, -16.66. So these are the fixed end moments due to the sway towards right. Now because D is hinged, so met 0 here, apply equivalent opposite and carry over, say this is plus 8.33. So then find out the initial fixed end moments. These are the initial fixed end moments, and I think this is okay. You do all these calculations and you will get the initial fixed end moments, then balancing of joint B and C, and finally what you do is calculate the final moments after completing the moment distribution. You complete this entire process of moment distribution, and these moments are called sway moments. These are called sway moments. These are called sway moments. Now after getting sway moments, find out the sway force, S force, force causing the sway of the frame. Now when we assume during the sway analysis, we only assume that the sway occurs towards right and there is no external load acting on the frame. If this is a frame, then no external load, we only consider this sway. This delta is the sway, and we know that due to this delta, both fixed end moments developed are anti-clockwise. Now this force is S, now here HA, and here HD. We already seen in slope deflection method how to calculate HA and HD by using the equilibrium conditions. So now to find S, so this is summation, again simply use Fx equal to 0. Here there is no external load. So this is S plus HA plus HD equal to 0. So we are assuming HA and HD always positive towards right. So S will be equal to minus HA plus HD. Then no doubt generally you will get the column end moments negative, and that negative becomes positive. So what is HA and HD? So this is MAB plus MBA divided by height of the column, that is 5, plus MCD plus MDC. This will be 0 no doubt, height of the column is 3. So substitute the moments, what you get here is MAB, MBA, this is MCD, MDC. So this value, this will be 0, this value will be 0 no doubt. So you substitute these values here and find out as force in kilonewton. And after getting this force S, the next step is to calculate the correction factor. So next step is to calculate N equal to, this is correction factor, and this will be RF divided by S. And then the last step, final moments equal to non-sway moments plus correction factor into sway moments. So with this formula, so finally you calculate all the moments, that is MAB, MBA, then MBC, MCB, MCD, etc. And after getting these final moments, then you construct bending moment diagram. So for bending moment diagram, these moments are to be used. because this is non-sway moments, these are the sway moments. That means if the problem is of sway type, then we have to carry out moment distribution 2 times. So it takes more time, double time. So no doubt few problems of even sway frames are simple, and only simple problems will take less time, but such type of problem will take larger time to complete the analysis. Now actually our syllabus of moment distribution is over, but I wanted to show few more varieties how to solve them. So suppose one case that we have not attempted is when a joint is subjected to concentrated moment. Then how to solve by using moment distribution method. Suppose you have a continuous beam, say like this, or say this is a hinge support. Then here there is a roller. This is also a roller support, and this is also a roller support. And say lengths are, say this is 5 meter, say 4 meter, again say this is say 4 meter. Okay, these are the lengths. And this is A, B, C, D. Okay, this is a beam. And now we want it and subjected to, remember here say clockwise moment of 30 kilonewton meter, and say here anti-clockwise moment of 20 kilonewton meter. Then we want to solve this problem by using moment distribution method. So here say as usual, what are the fixed 2 steps? First step, fixed end moments equal to 0 for all ends of the members, all because there is no load on any of the member. So only the joint B and C are subjected to concentrated moments. However, there is no load acting on the B, therefore fixed end moments are 0. And second step that we know, distribution factors K. So at joint, when we consider joint B, KBA equal to, this is 4 EI upon 5 divided by, this is, A is hinge. So KBA equal to 3 EI upon L, that is EI is constant, so gets cancelled. So directly I will write down 3 by L, L is 5, and C is continuous, so this is 4 by 4 plus total stiffness actually, stiffness of BA, that is 3 by 5 plus stiffness of BC 4 by 4, that is 4 EI by L, L is 4, so it is 4 by 4. So you find out this, and KBC equal to 1 minus KBA, so you will get this. And next you consider joint C, so at joint C, KCB is, this is also 4 upon 4 divided by, and this side it is 3 by 4, 4 by 4 plus 3 by 4. Because CD, stiffness of CD is 3 upon 4 EI. So you find out this. And then KCD equal to 1 minus KCB. So distribution factors we will get. And now let's prepare the moment distribution table. So only how to begin with is important. The rest of the procedure is same. There is no change at all. So here is the distribution factors we have to write down. Now write down the distribution factors calculated here, and directly you start distributing the moment. So if you want to check out the calculation part, say here distribution factor say 0.37 here, and this is 1 minus 0.37, 0.63, and here it is 3 by 4 1 divided by 1.75, say this is 0.57, so 1 minus 0.57, 0.43. So let's enter this 0.37, 0.63, 0.57 and 0.43. So no fixed end moment. So directly distribution means 30 into, this is clockwise. So 30 multiplied by 0.37. So 11.10. This is plus, remember, because clockwise 11.10. Then 30 into 0.63. This is 18.9. This is also plus 18.9. Then 20 into 0.57. This is 11 point, but this is anti-clockwise, minus 11.4. Minus 11.4. Then this 20 multiplied by 0.43. So this is 8.6 minus 8.60. So this directly balancing you start. Under such cases, you have started balancing. What is the next step is carry. Whenever we do balancing, then immediately this cannot be carried over, but this you can carry over. This you can, no, this also cannot be carried over because this is hinge. That is ruler, left end is hinge. Now, say carry over means by half value, this is minus 11.4 divided by 2. This divided by 2, 5.7. 18.9 divided by 2. Divided by 2. This is 9.45. And this is plus. Now this is plus and this is minus. So this is called balancing again. So do balancing. And then next carry over. Carry over only these two. This is minus, this is plus. Again balance. For balance, this is plus, plus, this is minus, minus. Then carry over. Minus, plus. Then balance. So this is carry over, balance. So this is minus, minus, this is plus, plus. And then again say there is a, if required, do this. See, this is plus, plus, minus, minus, and check how many cycles are required to vanish the unbalanced moment. So this is carry over, this is balance, and at particular stage when values, unbalanced moment becomes very, very small, negligible, that is 0.0 something, then you see, and here you write down final moments. Here you write down final moments. And what you will get, so here it is 0 because hinge, here also it is 0. Here both ends you will get positive, positive. Here you will get minus, minus. But sum of these two must be 30 clockwise and sum of these two must be 20. So that must be satisfied. And then you have to construct BMD. You can construct BMD, SFD, everything knowing this. So generally the nature only I will show you, the BMD nature. Say clockwise means, say here the moment developed at this end is clockwise, moment developed